GCDs and linear combinations. This is the conclusion where we're going to prove what we set out to prove. Okay, let's get to work. All right, the first point, let's recall what we proved last time. What we did last time. What did we do last time? Well, last time we showed that if H is a subset of Z, okay, and H with operation plus is an additive group, okay, group, then we have H is a multiple group, and there's no other types of additive groups, no other kind of additive integer groups. That's it. There's no other type. So that's very interesting. We proved that. We're going to use this theorem now. Okay. Now, our next point. What is GCD? What is the GCD? What does it mean? What is GCD? Well, I know what you're going to say. You're going to say greatest common divisor, but what is a convenient way to define this mathematically? All right, let's say we have two numbers, A and B. They're two integers. And, okay, we have the first part. D divides both A and B. So D is a common divisor of A and B. Okay, let's say this is true. Point one. Let's say this is true. And let's say we have another condition. If some other common divisor is another, D prime is another common divisor of AB, then D prime divides D. If this is the case, so if D itself is a common divisor of AB, and if all other common divisors divide D, then 1 and 2 here, point 2, imply that D is the GCD of A and B. And we can write it like this: D is the GCD of AB. So that's very, very interesting. Let's think about the logic of it. If D divides both A and B, D is a common divisor. But it's a special common divisor if all other common divisors divide D. If that's the case, then D is the greatest common divisor of A and B. You get it? Now, the next thing we want to do is we want to take H. This is the set of all linear combinations of A and B. So we take A and B, they're two integers, two special integers. We're going to choose them, okay, special integers. And we're going to form, x and y is anything in Z, all integers. Okay, we're going to take them to be any x and y. We're going to go through all the integers, and we create this set of linear combinations of all the combinations like this: xa plus yb with xy in a set of integers. Okay, so this is the set of all linear combinations of AB. We want to prove H is a group. Now, if we can prove H is a group, then we can then use our theorems that we proved last time to our advantage, and that's exactly what we're going to do. But first we need to prove that this thing actually is a group. It's not very hard to do. I'll do a little bit of it, and you're going to do the rest. So H is a group, so it has to have the four group properties, closure being one of them. So let's take two elements, xa plus yb in H, and x prime A plus y prime B is also another element in H. Let's add them together. Okay, the combination rule is plus. Let's add them together. We have x A plus yb plus x prime A plus y prime B. And this is x plus x prime A plus y prime B. Okay? Let's write this a little bit better. And of course this is an element of H. So yes, closure is good. 2, associativity. Well, plus is associative, so that's all I need to say about that. 3, inverse or identity. Well, you can finish that. Hint, take x and y to be both 0. And you can finish this one, inverse. For every xa plus yb in H, there is an inverse. Find the inverse. I want you to do that, okay? You do this. I don't think it's very hard, but it's a good exercise. It's quite interesting to do. It's always interesting to prove that something's a group. So go ahead and finish that. Great. So we're down to the next point now. All right. We have proved that H is a group. So we're up to point 4 now. Okay. H is a group. Group of integers with operation plus. All right. If that's the case, then we can now use this theorem here. If H is a subgroup of Z, then H is a multiple group, dz. So therefore, H is dz. H is a multiple group. Every element of H is a multiple of D. Let's examine the implications of this. What are the implications of this? Okay, great. So let's think about this. What are the implications? It has many implications. So I'm going to look at two of the central implications that we need. That's going to give us the theorem that we want. All right. First of all, the first implication is that A and B are in H. This is not entirely obvious. It is after you see it, but we say that linear combinations of A and B are in H, but A and B themselves are in H. And how do I know that? Well, if I take x is 1 and y is 0, then xa plus yb, this gives me x, and that's an element of H. And now if I take, this is A. And now if I take x is 0 and y is 1, xa plus yb, this is b, and b is an element of H. So yes, A and B are both in H. But since H is a multiple group, A and B must be, look at this, beautiful critical point. A and B must be multiples of this D. So A is PD, B is QD. Therefore, D is a common divisor of AB. Now, you see, my friends, you see where this is going, right? I bet you can see where this is going. Come over here and you see, well, how do we define greatest common divisor? Well, 2 steps. D is a common divisor of AB. The next step, any other divisor of A and B will divide, any other common divisor of A and B will divide D. So I've done the first part. I have done this. This I have done already. Now, it's done. Now I need to show this. Okay, and if I can do that, then I have proved that this D is very special. It's the greatest common divisor of A and B. So that's point 6. Let's work on that. All right. Since since H is a multiple group, it must be that D itself is an element of H. Therefore, D must be expressible as a linear combination of A and B. So it must be that D is XA plus YB for some X, Y, and Z. How do I know that? Well, you know, it's the way we define H. H is all linear combinations of A and B. But we know that H is a group. We proved it here. H is a group. And so therefore H must be a DZ type group. Therefore D has to be an H, and D must be expressible as a linear combination also. So what does that mean? Therefore, look at this. Look at this, it's very interesting. If some D prime divides both A and B, look, it divides A and B, therefore it must divide D. You say, I don't understand. I don't understand. Think of it. Look, D prime, if D prime divides both A and B, then it's got to divide D. This is going to be a multiple of D prime. This is going to be a multiple of D prime. Therefore, D is a multiple of D prime. Therefore, any other common factor divides D. And so what does that mean? We put it all together, 7. Okay. We take this definition. What is GCD? GCD definition plus, then we put this here in here, 5.5, that D is a common divisor of AB. We proved that. And now we add 6, that all other common divisors divide D. So therefore this implies D is the GCD of A and B. How's that for beautiful? And so we can now state the theorem. If the GCD of A and B, if the GCD of A and B is D, then there exist two numbers, x, y, that are integers, such that xa plus yb is D, the GCD of A and B. Well, we did it. We proved it. Okay? We proved what we set out to prove, that the GCD of A and B is expressible as a linear combination of A and B. We proved it. Okay? There we go. So therefore, the GCD of AB is expressible as a linear combination of A and B. Beautiful. We proved it. I think this proof is spectacular. It's wonderful. But we're not yet finished. I have some comments to make. We still have some things to think about. What if the GCD is 1? Let's say GCD of A and B is 1. The numbers are coprime. They have no factors in common. Well, according to this implies that xa plus yb is 1. There exists these two numbers, x and y, such that this is true. Now let's look at it the other way around. Suppose there exists x, y, such that xa plus yb is 1. Well, any factor, any common factor of AB must divide 1. Okay, let's say A and B have a common factor G, let's say. Well, G divides A, G divides B. Therefore, G has to divide 1. But the only number that divides 1 is 1. Okay? Therefore, the only common factors of A and B is 1. Therefore, okay, this implies A and B are coprime. And here we get to the final point, which I think this final theorem here is very important for solving problems. We're going to use it very soon. This is a very important theorem to remember. If A and B, or actually I'm going to write it using if and only if, A and B are coprime, if and only if xa plus yb is 1 for some xy that are integers. This is the main thing. This is the thing I'm getting at. This is very cool. A and B are coprime if and only if there exists two numbers x, y such that I can write a plus b, xa plus yb giving me 1. That's really cool. Now, I have some other comments I'd like to make. Let me go back over here, make a little bit of room here. I'd like to make some further comments, just something for you to think about. All right, this has been kind of a long journey over many videos, so I want to give you some more to think about. So we saw before, we proved it over here, we just did it, that if D is the GCD of two numbers A and B, then we have xa plus yb is equal to D, right? And we know that H is dz. So therefore, A, B generate multiples of D. Okay, so for example, if two numbers have a GCD of 3, okay, like for example 6 and 9, the GCD here is 3. So this, if all the linear combinations of this will generate multiples of 3, 0, 3, 6, and here minus 3, minus 6. Okay. If I take every possible linear combination, x times 6 plus y times 9, I'm going to get the set of multiples of 3. That's very interesting. You should think of it that way. That's very cool. And now what if the GCD is 1? They're coprime. Well, in the case of coprime, then xa plus yb is 1, and my h, all linear combinations, is going to be the set of multiples of 1, and that's exactly said. So AB, in this case, generate all z. Here it generates some z, and in the case of two coprime numbers, they generate all z. This is a good way to characterize the magic power behind coprime numbers. I want to leave you with just two little exercises. 1. Can you find two numbers that generate the set of all evens? And here too, this is something else you should think about. Can you find two numbers, A and B? Two numbers here, A and B. Okay. Two numbers A and B that generate the set of odds. Think about this. Get back to me. Write about it in a comment. I'd like to hear your opinion about these two problems. Click like on the video. Hang on for more stuff coming soon.